And with that, I think that we can turn it over to our speaker, Dr. Laura Johnson from the National Center for Water Quality Research. We have had Dr. Johnson here in the past, who has given us a summary of research, the nutrient data from the year before. And I think last year was the first time that we asked her to come in January so that she had a full year's worth of data to present. And I think that worked out really nice. So we're looking forward to hearing a summary of the 2020 data.
Awesome. Hi, everyone. Can you see my screen? Yay. Very good. Okay. So, well, yeah, I feel like this is our annual event of me making it to you guys to be able to talk about what's happened in the past year regarding the bloom. And so this year I'm going to basically do the same thing. However, because of a couple of other meetings, and I apologize in advance to Sandra, who's on the call too, because she's seen this already before, I thought I'd show you a couple of what I'm calling here other interesting tidbits that I thought you guys would like to see, just to sort of spice things up a bit. All right, and so I'm just going to move on. I am theoretically going to move on. There we go. Okay. So just as a quick reminder, since I've spoken with you guys an awful lot, I don't feel like I need to go into that much detail about our monitoring program, but I did want to remind you that we monitor lots and lots of different places. We're at 22 different locations, and in this map you can see that I've basically color coded the dots so that the darker dots are our oldest and most long-term stations, and the whiter the dots are, the newer stations they are. And so you can see the Maumee and the Sandusky being our longest term stations where we've been collecting samples for water quality analysis. And then basically a bunch of very, very small subwatersheds in the Maumee River watershed that are some of our newest stations. And then of course the Huron River as well. At these sites, if you went to any one of these dots, no matter what their color is, what you would essentially see is a building beside the river where we're collecting samples using an automated sampler. You can see, I'm going to see if I can make this a pointer that you guys can actually see here. Ah, perfect. You can see that the ISCO automated sampler here. So basically that's a refrigerated sampler. We pull samples 3 times a day all year round. So even with the icy weather and everything, we're still good at getting our samples in. Retrieve them every Monday, and then we bring them back into the lab. You can see a picture here of Barb for analysis of all the major types of nutrients as well as suspended solids. However, I routinely only talk about phosphorus. I think I have one slide on nitrogen in here for you all, so we can mix things up a little bit. But I almost always talk about phosphorus because that's what's of interest in Lake Erie. And so I'm going to start with all of the Maumee River data, primarily because that's the data that drives the bloom size. And then I'll show you a little bit of our other data as well. So in general, these should be very familiar figures to all of you. These are the Maumee River phosphorus concentration trends. And so in this figure, this is for this March through July time period. And each dot is a different year. This line is a 5-year running average, so you can see the trend. And then I also have the gray lines on here, which are for the dissolved phosphorus here is the concentration target set by Annex 4. And for this is for total particulate phosphorus, it's essentially a calculated concentration target from essentially the total phosphorus and the dissolved phosphorus targets. And basically what you see is dissolved phosphorus has that U-shaped pattern, right? So dissolved phosphorus being that phosphorus that makes it through a filter that you can't see, that's so bioavailable and easy for algae to use. And that these changes in concentration correspond to the changes in the bloom, observations of bloom occurrence in the lake, where we had blooms before, they went away through the 90s and then returned in the 2000s. For particulate phosphorus, however, we tend to see this decreasing trend from the 80s to the 2000s, which isn't a huge surprise because this is particulates, and that's when there was a lot of effort in trying to control soil erosion on farm fields. So so we had this big decrease through the 2000s, and really not a whole lot of change from the 2000s to today, except for, you can see I have at the very end, which was the 2020 year, you can see, is a bit higher than average, despite basically what we were seeing back in the 80s. I should also note, if you have any quick questions for clarification's sake, I don't mind if you wanted to jump in, but it might take up some time for questions at the end. But then we can also look at loads. And loads is when we take those concentrations and multiply by flow, and our loads show us similar but not exactly the same story. And I'll tell you why in a minute. But basically, you see a very similar pattern with dissolved phosphorus, except that it seems like dissolved phosphorus has just been continually increasing since about 1990. And then you can see in total particulate phosphorus, there's that downward trend, but loading of even particulate phosphorus is is increasing a little bit higher. These same things, each bar here is a different year, the lines are the different targets. But what's interesting about these loads is that you can now see how variable you can get from one year to the next. And so I wanted to point out, these are the years we talk about a lot, from 2011 to 2012, where it's this huge year, really big bloom year, lots of loading for phosphorus, to 2012 when there was a drought year, very little loading of phosphorus, very small bloom. Again, I noted here is 2015 to 2016, which are essentially very similar scenarios. The question here is, for particulate phosphorus, I just showed you that concentrations had leveled off over the last decade. So why do we have this increasing load trend? Same thing really with dissolved phosphorus. And the real reason for that is because if we look at flow from the Maumee River, a stream flow volume has basically been increasing through this period of time as well. In this scenario, this gray line is not any sort of target, but rather that's that 2008 year, you can see it pointed here, of which if we get beyond that, we would probably not be able to meet some of those Annex 4 loading targets. So you can see in 2020, our flow is lower than it had been, lower than average, but we still have this increasing trend, which is what matches, it's like almost weirdly well with the loading that we see in an increase for particulate phosphorus. I will note that you can still see those 2 years where you go from really high flow to really low flow, 2011, 2012, 2015 to 2016, that correspond to these changes and observations in phosphorus as well. Well, this is all great. I can point out every year where it goes from high to low for you if you really want. It'd probably get a little bit dull after a while, but the real way to look at this is to correlate the two together. So this is just dissolved phosphorus here, the load, versus that stream flow discharge from the Maumee River. And you can see that from 2000 to 2018, these are really tightly related, meaning low flow, low loading, high flow, high loading, right? Your typical sort of correlation chart. And at this point, you should be thinking, well, Laura, I've seen you present this even last year. And so this is just kind of a reminder of what I said last year. If you didn't remember, then it's a good thing I'm going over it again, because you're going to want to remember it perhaps. The nice thing about this figure is I can show both targets. If you remember, Annex 4 has a concentration and a loading target. This is the loading target, and the moving target is the concentration. And if we remember from last year, the only reason I say this is a great correlation up to 2018 is because in 2019 we had lower than expected loads. We had really, really high flow. You can see it's way up here on this upper end of the graph, 1, 2, 3, right? One of the very highest flows we'd ever had, but our loading was actually a little bit lower. And so we ended up having a 30% lower than expected load for 2019. And the big questions, and this is also a reminder to you, is, well, why was that? Well, in 2019, if you recall, that was when it basically rained all year, and we had a much lower planting. You can see that in this vegetation index, where we compare July and August of 2018 to July and August of 2019. What this also meant is that we had less phosphorus application, substantially lower, both in terms of commercial fertilizer amounts, as well as manure applications from March through May. And so if we summarize this very quickly and very succinctly, what this really says is that phosphorus application, the process of that application, fertilizer and manure, which would really mean timing or placement in this scenario, right? Like that actual application process has a larger influence on loads than at least what I would have expected. 30% lower phosphorus, a 30% phosphorus reduction associated with these activities is way higher than I would have expected. And it's probably higher than what you think when you keep hearing, we have to have patience to see these changes, right? What it means is that we might be able to start to see changes faster than we would expect if we were able to maybe better understand what parts of timing replacement of fertilizer plays a role here. I also wanted to point out, though, that this lower dissolved phosphorus, lower than expected, ended up leading to a lower than expected bloom as well. So in 2019, if you remember, we had a 7.3 on our ultimate, I think it was 7.3 on our ultimate bloom severity index. And if we had actually, if we had the bloom based off of what we would have expected for DRP loads, we would have expected something more like 2011, somewhere around a 9.9 to 10. So not only did we see these lower applications, meaning something about the land, but we saw the effect that it had on the lake as well. Still a very big bloom. 7 is still not at all the bloom size we want, especially how scummy it was around Maumee Bay, but I thought that was interesting. So let's move forward here. Although we had this big decrease in dissolved phosphorus, now I'm showing you total particulate phosphorus, remember? So now we're talking about the phosphorus attached to the sediment. In 2019, it was as expected. So it was the second highest total particulate phosphorus load that we'd ever had. But when we actually pull these figures together, then we note that 2015 is also an outlier, but it's vice versa. Whereas 2015 here had a lower than expected particulate phosphorus load, but the highest dissolved phosphorus load, right? In fact, it was almost the same percentage decrease. The difference being that when we look at the bloom severity index, in 2015, it was one of our very highest blooms, largest blooms that we've ever had. It was a 10.5 on our 0 to 10 scale, which is supposed to be impossible, right? And this same reduction in 2019 led to a lower bloom. It was around 7. So this starts to show us that the form of phosphorus is really important. But I think we start to see that again this year. And so this year in 2020, I highlighted it because these figures look awfully similar. In 2020, we had much lower flow. I pointed that out in the previous figure. We were about a 3 instead of all the way up here at a 5. You can see that dissolved phosphorus rebounded back to where it was, right? So it's exactly where where we would have expected it to be based off the amount of flow. Turns out it's just a little bit above our loading target. So we weren't expecting a very large bloom this year. But what's intriguing is this year particulate phosphorus load was about 45% higher than expected. And this should be potentially concerning. This is also redundant with what I just showed you. But if you think about 2019, we had these fallow lands full of weeds, and one of the best ways to control a really heavy weed burden is to till the ground and work the ground a little bit. And so that's what we think we're seeing the response of having such a hard year basically coming out to play in our particulate phosphorus loads. Hopefully that all makes sense so far. So what did we actually see this year? And this is what I pulled from our seasonal assessment that Rick Stump put out from NOAA. And this is basically a comparison of a similar 10-day period of time. This is August 1st through 10th of 2019 versus the 21st to 31st of 2020, which would be basically the largest sort of 10-day average period for the 2020 bloom. And what you see here is that it looks like the bloom maybe covers more geographic area, but all these blues over here, these cooler colors, you wouldn't have been able to see that bloom, right? So like this is here because we have good satellite imagery and be able to detect it. You wouldn't be able to see it. Really, it's these reds that form those scums. And you can see in 2019 how bad and how dark those reds were right around this Maumee Bay area, right? Which is where we heard it was especially bad. Didn't really have that same scenario occur this year in 2020. Hopefully that lines up with what your guys' observations were and experiences were on the lake. You know, it was a much milder bloom this year. And so this is the final bloom severity forecast that, or number that came out. You can see the 2020 ended up being a 3 out of 10. It was forecast as a 4.5. So the forecast was overshot clearly by a little bit here. What is interesting is thinking about why that occurred. And so I just want to remind you guys that when we do these forecasts, they're an ensemble of different models that go into determining how big that bloom is. And you can see one of the models got it right? This is pretty close to right on right here. And a lot of the models didn't. And so the one thing I just want to point out is that some of these models are focused on total phosphorus, which is both the particulates and the dissolved phosphorus. So if we had a much higher than expected or a higher than normal particulate phosphorus load, it would make that TP load much higher. And doing so, that would overshoot the bloom. So what I think that we'll learn from this year is that once again, the form of phosphorus is important, and there might need to be some updates to these forecast models now that we're starting to see some divergences in how the loading's occurring from one year to the next. Okay, so I'm going to move on to a different topic where there may be any quick clarifications. Everything's making sense so far? All right, good. Okay, so I wanted to show a little bit of results from some of these newer stations that we have on board now. And so I've highlighted these in yellow. I'm actually only going to show you Wolf Creek, South Turkey Foot, and West, along with all of these other Western Lake Erie Basin sites. Now I'm going to show you a bar chart. I'm going to start at the River Raisin, and then we're going to move around the Maumee, its subwatersheds, hit the Portage, and then get Sandusky and its subwatersheds, and then end. So as you're looking at the figure, think it's a loop-de-loop kind of working around, okay? And so what do we see? This is for 2019 because we haven't quite finished all the 2020 loads yet this year. It's a long process of QCing, which I prioritize for Maumee, but not for everywhere else. So these are 2019 data. But when I point out, this is dissolved reactive phosphorus, and you can see I said we start at Raisin, do Maumee, its subwatersheds, Portage, then Sandusky and its subwatersheds, right? So you can move across. Well, the general thing that we typically see when I put together these types of figures is that the River Raisin and the Tiffin River tend to be lower than the Maumee and some of its other subwatersheds. And usually that's because they have lower agriculture and they have a different soil type. So it's not a surprise. The Blanchard River here, we're really close to the wastewater treatment plant in Findlay, so it tends to be a little higher. Everything else is kind of the same. But I wanted to point out a couple of interesting newbies on the block here. We've got Wolf Creek and West Creek. Now Wolf Creek, you can see is well below, as our residential area, okay? So Wolf Creek's up in the Toledo area. It's a tributary to Swan Creek, just off of Holland-Sylvania Road, if I remember correctly. And this is, if you looked at the watershed, it's basically all roads, some forest by the creek, and a bunch of houses, right? So it's such a small creek that there's no point sources going into it either. So we're talking primarily about urban non-point sources, which is a hard thing to get without any of these other influences, right? So when you look at this, what you see is that, well, Wolf Creek has like the lowest DRP concentrations across all these sites. It's primarily urban non-point source, a little bit of ag, but mostly everything else. And so that implies to us, one of the big questions we always have is, well, how much phosphorus is coming from Walmart's parking lot? I don't think that this has Walmart, but it has a little bit of some other shopping areas just near that 475 interchange over there. And so what you can see is that not a whole lot. I have popping in here, this is again that flow weighted mean concentration target for Annex 4, so you can see it's about half of that. But then if we move over, we get to West Creek, and West Creek's interesting because it's awfully close to that target, right? But it is 92% agricultural. It's like right smack dab in the middle of the Maumee, going directly into South Turkey Foot, which goes into the Maumee River. And so one of the questions is, well, why is West Creek so low? So the first thing that came to my mind is like, well, it's clearly not a lack of agriculture, which might happen at the Raisin and Tiffin in part. So then I thought, well, maybe it's a soil type issue, because I mentioned before, Raisin tends to infiltrate better, so we don't get as much dissolved phosphorus loss. And so here's my promised nitrogen slide. So here's nitrate nitrogen, and nitrate nitrogen tends to reflect agriculture very well as well. And you can see now River Raisin and Tiffin River are very similar to all the rest of them. And so is West Creek. Okay, so plenty of agriculture. There's plenty of ways for water to get into West Creek carrying this nitrate. And so then I was like, well, maybe it's a soil type issue. I was like, no, if anything, West Creek has even more of those really poorly draining hydrologic soil classes of C, D, or D, right? So these are like, you have to tile drain in order to be able to farm this area. So I don't have a great answer for you. I'm just basically wetting your whistle, interesting tidbits, right? That West Creek has lower than expected DRP, and we're gonna be looking into that because I think it could be some insights into how we deal with this whole phosphorus issue to begin with. And I'm kind of interested and excited about that. I'm gonna take a step back and think about Wolf Creek again. And I just wanna note that with the addition of Wolf Creek being a non-point source that is primarily residential and urban, it might help us open up this black box of mass balances. So remember, this is the Ohio EPA mass balance that is performed on the Maumee River using our data as well as other data that they collect. And just a reminder, what it shows us here for TP is that 88% of the phosphorus in the Maumee River is from non-point sources, so that land runoff, whereas 4% is from septic, and 8% is from permitted discharges. That includes combined sewer overflows, okay? So the challenge here is that when people see this 88%, they say, well, how much of that is from agriculture? And it's a hard answer to question to answer. We can go off of land cover and say, oh, well, based off of land cover, it would be probably 71%. If we did that, we would assume equal loading across all these land uses, which I just showed you is probably not really accurate anymore. We see that we get less phosphorus from our urban sites for non-point sources. And so using this Wolf Creek data, we might be able to better understand this by saying, you know, scaling it differently and say, okay, well, if we scale based off of the loads that we measured from 2019, also not perfect, but an example of how this could work, then we can show that actually a vast majority of these non-point sources are from agriculture and a much smaller percentage are coming from urban or other hard to define non-point sources. So I think that there might be some interesting ways to use this data. This might not be the perfect way to do it, but I think that there's things we can do here. So I want to give us a chance to chat about all of this. So the summary is basically that every year I feel like we're learning more about what's happening between the Maumee River and Lake Erie, or Lake Erie and other tributary inputs and that sort of thing. But so far it just seems like every year we're further finding out the importance of dissolved phosphorus, which is somewhat unfortunate because it's harder to control. 2020 bloom was milder than 2019, and the forecast slightly overestimated that bloom severity. We think it has to do with these differences in phosphorus form, and I would expect to see some updates this summer on that. New monitoring locations that we've added are helping us better understand those residential and developed areas non-point source. That's always kind of hard to answer when I get those questions, but also some of the variation that we're seeing in these sub-watersheds, maybe future research directions regarding the places like West Creek. I think that's it. So it's all my contact info if you have any questions. Now I will stop sharing so I can see all of your beautiful faces, and we can, there we go. Yeah, I can share a slide if we need to go back.
Great, thank you, Dr. Johnson. So one question that I have is, Wolf Creek is primarily urban. Are there any other tributaries that you monitor that would have a similar urban footprint? And is that, I guess, comparable to those, or is it potentially an anomaly?
That's a really good question. So we have the Cuyahoga River, which is somewhat similar, I would say, urban footprint. There's a lot more, there's very little agriculture and good amount of forest. Probably not quite so urban, probably a little bit more forest just of where we're located because we're in Independence. The results are very similar. The issue with the Cuyahoga is it's getting Akron's point source. So if you've looked at my long-term trends over time, you see that point source is sort of going down as they control that. And so it doesn't seem like it's an anomaly necessarily. It's just we're comparing a big river to a tiny stream, one with point sources and one without. So other than that, no, it's kind of hard to find a tributary that is in the Western Lake Erie Basin that doesn't have a lot of agricultural influence. This one's kind of handed to us in part because Ohio EPA was already monitoring it. So I don't think it's an anomaly, but it's a good question. It might be something worth looking into a bit more.
Thank you. Any other questions?
Laura, I was excited to see that you're starting to move toward breaking down that non-point source section of the nutrient mass balance. And I think maybe this question is more for Sandra, because I see Sandra is on the line. So we've got the non-point source, and then we also have the NPDES permitted portion as well. There's a lot of different types of NPDES permits, including stormwater permits, permits for animal feeding operations, if they happen to have an NPDES permit. Are those all included in that total for NPDES? Or how do you break all of those? How do you break those down?
Yeah, if you're looking at the nutrient mass balance, they put everything NPDES in that category. That being said, I think while the agricultural areas have NPDES permits, I don't know that there's that many of them that have active discharges. So, you know, it's not the same as a wastewater treatment plant where they're treating and discharging. And that's about all I can say about that, because I'm not that familiar with it in detail, but to my knowledge, they put everything NPDES in that category.
My understanding is that the challenge with some of those permits, especially like I know the challenge with trying to deal with the combined sewer overflows is that there's not, usually those are reported as volumes rather than in terms of phosphorus loads, which sounds kind of trivial, but like, so trying to get a good estimate for how much phosphorus is in some of that is a little bit tricky. I know that they use some existing data to be able to make those estimates, so that with similar data that I had also dug up, I think Northeast Ohio Regional Sewer District does a really good job of monitoring some of that. And so that is a really interesting point that you bring up though, Kari, because it would be worth touching base with Paul Gledhill just to see if, aside from like a CSO, if there's stormwater volumes that are included in that chunk that has a phosphorus estimate associated with it. I didn't think that there was, otherwise I wouldn't have done the sort of visual exercise, but I'm not really sure.
Okay.
Yeah.
And is there a plan in future nutrient mass balance studies to really break down the NPS portion of that? And I think we're at a good start with what Laura's already done. But is there enough data out there to begin to, I guess, try to determine where these sources are, whether it's from, say, an animal operation or row crops? Is there enough information out there to do that?
Well, they're working on, or they're trying to do, breaking up that non-point source. And as Laura was mentioning in her presentation, they've been doing it based on the land use percentages. So Laura, I'm sure Paul would be really interested in what you were looking at in terms of adjusting those, the assumptions around that part of what they're doing. That's really where their focus has been, adding more watersheds so that we can split the Maumee up a little bit and then separating out what's in the non-point source. I don't think there's that much concern at this time with the point source part of it. It's felt like that's pretty well under control, and there's not that much policy work that they would be able to do to improve it. It's still on their list of things to do to add permit limits as appropriate for some of those smaller discharges. But when you start talking about the fraction of the NPDES that doesn't already have phosphorus limits, it starts to get to be a really tiny proportion, because these are really, really small treatment plants. So it just hasn't really been their focus. And I'm sure you guys are well aware they're starting the TMDL process. And so some of these questions will work out as they go through that process.
And I don't know if using this one creek would be valid across all of the different locations that are used for the mass balance. You know, I'm talking about one location that's up in Western Lake Erie Basin, which I think could be informative through that sort of process. But I wouldn't say that you should necessarily use that for doing any estimates, say down in the Great Miami or maybe Lower Scioto or something like that. That's like land use and like everything just changes so much, and it might not be nearly the same type of comparison either. But I think it's intriguing nonetheless. Yeah.
Yeah, I'm intrigued that it's Wolf Creek, you know, this Wolf Creek watershed that you chose. Coincidentally, it has a big chunk of the airport in it. I mean,
Yep.
I don't know if it's an abnormal number of golf courses, but let's say there's a lot of, you know, golf and outdoor recreation fields in this watershed, that kind of stuff. Like, you know, things that just make you wonder what contributions, you know, are some of those things.
Right. And so sediment, actually, as an aside, sediment loading is actually pretty high. Like there's a lot of erosive capacity in that creek. We've had some challenges with our pumps getting buried and stuff like that pretty often. So just because it doesn't have phosphorus, we have to remember that there's water quality issues that we should be tackling and fixing that don't always have to be associated with phosphorus. So a lot of the things that Sandra was talking about, like, you know, stormwater or even the smaller treatment facilities, you know, keeping on top of those just to make sure that our water, like our local water quality also is good, is a good thing.
Well, there's local versus far field, right? What they would call near field versus far field. So some of these areas, there might be near field effects right there in the creek, right downstream of whatever the land use or the discharger is doing. And there's a well-established TMDL process for that if it's resulting in a use impairment. Then the far field is this issue we have with trying to assign load reductions throughout the Maumee to address what's happening in the western basin of Lake Erie. And that's still a process that is just being worked out. We have a first go at it in the domestic action plan, and they will be doing another go at that in the TMDL.
I have another question. So in the last domestic action plan, there were some estimations given for land use for each of the Huck 12s in the Maumee River Basin. How have you looked at how the data that you have collected in Wolf Creek compares to the load estimates for that particular Huck 12?
I have not done that. That would probably be a good thing to do, or at least send the data to Paul and let him do it, one or the other. Because I mean, basically my understanding, and Sandra would know too, is that they're using that exercise to sort of build everything off of for this whole TMDL process, which, you know, if you really think about it, makes a lot of sense. Because if you look at the different areas that Huck 12's cover, it's like, you know, there would be different issues to want to be able to manage depending on where they are. Not everything is necessarily trying to deal with an agricultural non-point source throughout the whole Maumee. I think that's smart.
Great, thank you. Are there any other questions?
Well, if there are any, feel free to email me, or maybe if you have someone you want to talk offline, that's fine to understand. I'd be happy to chat more about this in another way.
Great, thank you very much.